Thank you very much for the invitation. It's very nice to be here. It's also nice to give a talk with the PhD advisor in the audience, Vladimir Wapnik. Makes me feel a little bit like a student again. So I hope I will pass this exam. So I will talk about causal machine learning. And we all know about machine learning and about the great things you can do with machine learning. This is an example of what you can do. From the Amazon webpage. So this is the German Amazon webpage. If you search for this item here, which is called in English a glass or circular cutter, it's a device that you can attach to a window pane, make a round hole. Then Amazon will give you some recommendations of other items that you could buy to go along with it. So this is a real-world example. So like this balaclava, leather gloves, or down here a baseball bat, brand name Hooligan, and in between this one is curious. This is a Batman rucksack with bat wings. Now, of course, this is a great example where maybe you could say machine learning works and makes useful recommendations, but there are other examples where it doesn't work so well. And this is another example from the Amazon webpage. I should say this one doesn't work anymore. I think they fixed this one. The other one, I think, still works. And in this example, the person is shopping for a laptop rucksack. And then Amazon recommends that he or she should also buy a laptop to go along with the rucksack. And somehow this doesn't make sense. And if we ask ourselves why it doesn't make sense, then maybe it's the case that in some sense, if we have the laptop, this is causal for wanting the rucksack. But if we have the rucksack, I don't know, it doesn't feel like it's a good cause for buying a laptop to fit into the rucksack. So it feels like, so certainly if you look at the shopping database of Amazon, you will find a strong statistical dependence between these two shopping events, whether someone bought a laptop or bought a rucksack. So on the statistical level, this dependence is there. So in a sense, if we do machine learning on this data set, it's valid that we come to this conclusion to recommend this thing. But we have ignored what brought about these statistical dependencies. So there's an underlying structure that's responsible for creating these statistical dependencies. And you already heard from the previous talks about causality that such a structure can be a causal structure. And in this case, it seems quite clear that the laptop is causal for wanting the rucksack. So there's this structure there, but if we just do machine learning, we have ignored it, and we have come up with a stupid result. And there's this quotation here. It says, imitate the superficial exterior of a process or system without having any understanding of the underlying substance. So in some sense, if we just train a machine learning system on data generated by this process, this is what we're doing. And this is actually a definition of something called a cargo cult. So you probably heard about cargo cults. This is something that was discussed by Feynman in his memoirs, The Cargo Cult. He writes about cargo cult science. The cargo cults are this some kind of pseudo-religious practices that were practiced in Pacific tribes after World War II, or maybe already before. They were associated with performing certain actions that these tribes thought were connected to receiving cargo. So, for instance, maybe they observed that if you get cargo from the Americans, there's a landing strip and there's people waving flags when the planes appear. And then later on, when the planes stopped appearing, they would still try to wave flags and build fake landing strips and things like that. So they had learned a correlation or a statistical dependence, but it somehow didn't work anymore. So I'll come back to this probably in the conclusions. Okay, so here's another example where there's a difference between causality and statistical dependence. And I think you all know this example. Storks deliver babies. So this is if you look at the different European countries and the frequency of storks and the human birth rates, you find a strong statistical dependence between the two variables. But of course, nobody would, in their right mind, would suggest that we could increase the human birth rate by having more storks in a country. So these quantities are correlated, but the causal story is more complicated. And from the point of view of Reichenbach, and I think this was already mentioned before by Dominik, So according to Reichenbach's principle, if there's a statistical dependence, then there is some kind of causal explanation for it, but the causal explanation can be more complicated. So the causal explanation in general is one of these three. So if x and y are statistically dependent, there's a third one that causally influences both of them, and as a special case, this third one might coincide with x or y. And Reichenbach moreover said, so we're talking about the classical world here, this is not about quantum mechanics, Reichenbach moreover said that z, this third variable, screens x and y from each other in the sense that if we condition on z, x and y become independent. Okay, and there's a beautiful theory that you already heard something about in Dominic's talk, so maybe we didn't coordinate sufficiently, so there'll be a little bit of repetition, but I hope not too much. So there's a beautiful theory developed by Pearl and others where we assume we have a set of variables. We assume they are connected by a directed acyclic graph. In this graph, arrows represent direct causal links. And on the graph, on each node, we have a function which computes the random variable associated with that node from its parents and a variable ui, which is a noise variable. All the randomness comes through these noise variables. The rest is deterministic. And these noise variables we assume to be jointly independent. Now, this is a way to generate a joint distribution of all the observed variables. In fact, you can generate any joint distribution of these variables with such a set of functions, such a graph, and a set of independent random variables. So it's just you could say it's just a different way of generating or of writing a joint distribution. But it turns out this way of writing it contains more information because it directly tells you what happens. So this is an assignment operation. So this directly tells you what happens to a variable if something changes on the right-hand side. So you can think of this as a description of a statistical model which not only explains the observational distribution, because certainly if you plug in the distributions of these UI, you get as a consequence, you get a canonical way of computing the joint distribution. So this is a way of not just explaining the joint distribution, the observational joint distribution, but also a set of interventional distributions. So distributions that tell you what happens if we intervene or if we change some of these functions. So it's a richer description than a standard statistical model. And it's a description that also allows you to make statements make causal statements. And it turns out that this graph, along with the distribution, satisfy an interesting condition, which is called the causal Markov condition. So it turns out that from the topology of this graph, we get certain conditional independence properties. So there's an implication from certain graph properties to certain stochastic properties, in particular these ones here. I think Dominic also mentioned this. And it turns out we can use something related to this to infer the graph from statistical data. Namely, if we assume this is not just an implication from graph properties to stochastic properties, but if we assume that this is an equivalence, so people have argued whether we can assume this or not, this is called faithfulness. If we assume this is an equivalence, then from these stochastic footprints, so when we observe certain conditional independencies, we can infer certain topological properties of this graph and learn something about the causal structure. So this is, and by the way, I should say this object is also called a directed graphical model. And here I have a brief overview of the different approaches people have taken to infer something about the structure of this graph from purely observational data, which in some sense you could say is the most difficult question of causal inference. So this is what I just briefly mentioned, the graphical approach or constraint-based approach. So the assumptions for this approach are the noises are jointly independent. There's this assumption of faithfulness that I just mentioned. So we assume that these conditions, observing a conditional independence does not mislead us about the structure of the graph. It's actually a characteristic of certain graph properties. And the method then builds on conditional independence testing. And in some sense, the intuition, you could say, is think of you have such a complicated graph structure. Now we feed in some independent noise at each node. So there's a noise variable at each node. And then we track how this noise spreads through the graph. And then we're allowed to ask conditional questions. So we sit on one node and say, what do we know at this node about this other one that we don't know from this third one? So we can ask all sorts of conditional questions, and intuitively it's clear this tells us something about the connectivity structure of this graph. Now, we have worked a lot on this kind of problem using two sets of alternative approaches. One, Dominic already mentioned before, the additive noise models. So I'll say just a little bit about this in one of the next slides. So here we make a restriction that this noise enters these functions up here only additively. So the class of functions gets smaller, and then it turns out we can solve some of these problems by regression and unconditional independence testing. And the second set of methods builds on something we call the principle of independent mechanisms. And in this case, we need a different kind of independence assumptions. So we don't assume that the noises are independent, but in some sense that needs to be formalized that noises and functions are independent. And if we assume this, then in some sense, not only do these noises pick up information about the topology of this graph, but also they pick up information about the functions that they pass through as they spread through the graph. Okay, so this is a little bit more information now about this principle of independence of mechanisms, or independence of cause and mechanism. So in the simplest case, which is the two-variable case, which actually is the case that using constraint-based methods we cannot solve at all, because certainly a conditional independence statement always involves at least three variables. So if we have only two variables, we can't solve this at all. So this is the two-variable case. This is how the graph looks in that case. And in this case, we're making the assumption that, and I'll say a little bit more about this, that the distribution of the cause, which is our input, in this case, we can identify this noise variable and this random variable. There's nothing interesting happening. And the conditional of effect given cause are independent. So I'll show you a picture first, or actually two pictures, to give you an intuition what this could mean. So this is a picture from an art exhibition somewhere in Germany. It's called a Boucher chair. And this chair is called a chair, or maybe I should say, so in general, whenever we look at some object out in the world, then our brain makes the assumption that the process through which the information from the object enters our visual system in our brain and the information about the object itself, or the structure of the object, are independent. So the cause and the mechanism, so the cause is this 3D arrangement of metal in the world. The mechanism is the projection into our brain, how it's processed, etc. These two things are independent. In particular, we're looking from a generic viewpoint, and we can violate this assumption in this case by looking through this hole. And if we look through that hole, then suddenly the object starts looking at like a chair. So in a sense, perception fails because we see an object which isn't there. So in some sense, it's plausible that our system makes this assumption. And there's another example. There's this strange object down here in this painting of Hans Holbein. And if you move very far to the side, you can see it's actually a skull. So it's another example. This is another example of this sort of generic viewpoint assumption, as some people in perception sometimes call it. And so we try to formalize this kind of assumption. And in the simplest possible example here, we have two variables, x and y. We actually assume that this function sort of computing y as a function of x is deterministic. And if we then assume that we start with some generic input distribution over x, and if we assume, in a sense that I will tell you on the next slide, that if this function here is independent of that distribution, then it turns out that the output distribution carries information or a footprint of this function. Because intuitively, wherever this function was flat, the output distribution or the output density takes large values. And one way to formalize this, without going into too much details, is we postulate. So we construct two random variables, one random variable, and both of them on the probability space 0, 1 with Lebesgue measure. One of them is just the density of the input distribution. The other one is a certain function of x. So this is just x between 0 and 1, namely the logarithm of the derivative of x. And it turns out that these two, if we now postulate that the covariance between these two random variables vanishes, then we can prove that in the backward direction, assuming that the function is not the identity, so it's a non-trivial problem. This is a nonlinear function. We can prove that the covariance is strictly positive in the backward direction. So we have an asymmetry. Okay, so this was the first idea. The second one, also briefly mentioned by Dominic, is restricting the functional model by additive noise. And just to motivate why it's important or why it's actually necessary to make this kind of restriction, let's just think for a second what would happen if we made no restriction whatsoever. So again, in the two-variable case, so this is our graph. Suppose x is causing y. And now assume we use the general functional model. So y is some general function of x and the noise variable. Now, as before, so I should actually say x is a function of its noise. But since x has no other parents, we can again identify it with its noise variable. And then x becomes a random variable in its own right. And the assumption that the noises are independent now turns into the assumption that x and this noise, which goes into this function, the noise u, are independent. So we have this kind of model, this kind of independence assumption. So now we can think about how large is the space of distribution that we can explain this with this. And in particular, if you think about it for a second, suppose the noise variable only takes discrete values, d different values. Already with such a relatively simple random variable, we can generate an overall mechanism that randomly switches between a set of d mechanisms. So because this is a function of two inputs, these are d functions of one input. And of course, d could be arbitrarily large, or it could even be a continuous variable. So in a sense, we could, with such an assumption and no restriction on f, we can switch between a continuous number of different mechanisms, turning x into y. So that seems to be hard to learn such a model from data. Therefore, we need a restriction, and in particular, in our case, we make a restriction on how u affects this function f. So in some sense, we assume that u affects this function f in a simple way, and one way to do this is to use this additive assumption. Okay, so this is very briefly one result that one can prove for this setting. So if we assume additivity of the noise and independence, as I told you before, and now if we assume that such a model exists in the forward and in the backward direction, then it turns out there's a very particular link between the densities of u, of x, and this function f. So they have to satisfy some complicated differential equation together, for which we can show it only has a three-dimensional solution space. So out of the space of all possible densities on u and x and all possible functions f, only a three-dimensional subspace actually is such that we can explain this joint distribution with such a model in both directions. And these special cases for which it works are actually cases where it makes sense. For instance, if both these distributions are Gaussian and the function is linear, then it's already known that we can do it in both directions. Now, I told you briefly about two ideas. We tried them both out on some data set that we have collected of cause-effect pairs. And I don't want to go into details on this, but the message is that essentially we can solve this problem with accuracy 70 or 80%, roughly, on these data sets where the accuracy depends on how often we force the algorithms to decide. So if we require that they always decide, then we are sometimes outside of this zone of random guessing, sometimes not. I don't want to interpret too much about this, but the problem can be solved better than chance. And the same methods can also be used to classify the direction of time in time series or videos. Now I want to come to the second part of my talk, where I want to think about how can this kind of knowledge about causality inform how we should be doing machine learning, or what we should be doing differently. And this is, I have two things to mention in this context. The first one I'll do very briefly, because I think I mentioned this one 2 years ago when I gave a talk in Moscow at the previous event. Second one is new, so I'll talk about this one in more detail. So the first one is connected to semi-supervised learning and transfer learning and covariance shift. And it's based on the following assumption. If we do machine learning, then sometimes we learn causal problems, and sometimes we learn anti-causal problems. By this, I mean sometimes there's our direction of prediction. So let's assume always x is our input and y is our output. Sometimes our direction of prediction is aligned with the direction of causality. And such examples, for instance, you can find in bioinformatics. But sometimes, and maybe even more often, in typical applications, the two directions are opposite. So sometimes we try to predict cause from the effect. So for instance, in handwritten digit recognition, the cause is a class label that a person writing a digit wants to write, and then the effect is the actual image of the digit, and is produced by some complicated process, which we don't worry about because in the end we only look at statistical dependencies between class labels and images. Okay, and it turns out that whether we learn causal or anti-causal has substantial implications for what is easy and what is difficult in machine learning. In particular, for two problems, semi-supervised learning and covariate shift. So in a certain sense, maybe I can briefly explain this. In a certain sense, semi-supervised learning is easy or is possible in the anti-causal direction, whereas covariate shift is easy in the causal direction. So in the causal direction, it turns out that it's reasonable to assume that this conditional P of y given x is invariant under changes in P of x if we make this assumption that I mentioned before, that the distribution of the input and the mechanism are independent. So if these objects are independent, if I change the distribution of the input, there's no reason to believe that the mechanism will change. And then the covariate shift assumption holds true. In the opposite direction, that's more difficult. Now, for semi-supervised learning, it's also interesting. If we think about semi-supervised learning, so we want to learn x to y, but in semi-supervised case, we want to improve our estimate by getting additional data from P of x. Now, learning means estimating properties of P of y given x. So we want to learn x to y, estimate such properties. Now, someone gives us more information about P of x. This can only help us estimate this thing here if in some sense there's a dependence between these two objects. Now, as I mentioned before, in the forward direction, in the causal direction, if we make this assumption, then this tells us directly these two objects are independent. So we would assume in the causal direction, semi-supervised learning should be impossible. And actually in the backward direction, we would assume that it's possible. We don't claim it always has to work, but at least it should be possible. And it turns out this is very much consistent with analyzing benchmark studies that other people have performed in the area of semi-supervised learning. And it's also interesting to think about how to interpret known assumptions that people have come up with to justify semi-supervised learning. Actually, all of these assumptions can be interpreted as links between a distribution of x and a distribution of y given x. So they all talk about a dependence between these two objects. Okay, but now I want to talk about this last application, which is from astronomy, which I'm quite interested in currently, and I think also nicely fits with this kind of causal thinking about machine learning problems. And this is related to a satellite, the Kepler satellite, which was launched, I think, 2009, and orbits the Sun. So it doesn't orbit the Earth, but actually the Sun, trailing behind the Earth's orbit, and which was looking at one sector or one part of the Milky Way in a star-rich area about 3,000 light years deep. And it was looking for 4 years overall, observing or looking closely at 150,000 stars in this field in the constellation Cygnus. And it takes a picture every 30 minutes. The exposure lasts 30 minutes. So we get a time series of such pictures. Each picture, so this is a set of CCD imaging chips and their location, what they look at in the sky. Each picture looks like this. So we have a time series of such pictures. And from these pictures, we want to find exoplanet transits. So an exoplanet transit means we want to find these lucky cases where there's a star somewhere far away, and one of the planets of the star passes in front of the star as viewed from the Earth. So of course, this is maybe not so likely. So if you think about if you wanted to detect our planet from space, then you would find out that it should be only detectable from about 0.5% of all directions geometrically. The signal would last about half a day, because that's the speed of the Earth and the size of the Sun. And the size of the signal would be about 10 to the minus 4, because the Sun is about, the diameter of the Sun is about 100 times the diameter of Earth. So, and this goes quadratic. So we would assume, if we are in such a lucky case, that the brightness of the star or of the combined system stays constant, then there's a little dip that lasts for a certain while, and then it's constant again. And the Kepler satellite has found quite a few planets, but probably it's still fair to say nothing that's quite like Earth and Sun. Now, the problem in the whole problem is, the problem with the whole approach is that both the spacecraft or the telescope and the stars have a lot of intrinsic variability, much more than we thought, because when we observe these things from the ground, then we have all the atmospheric disturbances. But if you watch from sky, you actually see how variable stars are, maybe more than we used to think. And so both the spacecraft and the stars vary, and this leads to changes that are often much bigger than the signal we're looking for. Okay, so here's now a little bit in more detail the problem that we want to solve. So here's our transit. So let's assume Q, this is the random variable, or the quantity, the observable that we want to reconstruct. So it's the brightness of the combined star-planet system. Now we assume that, of course, we don't measure this thing directly, because all our measurements are influenced by these noise sources that come from the instrument. They come from various things. It comes from, I don't know, temperature fluctuations. It comes to a large extent from tiny pointing errors, because this instrument, it points exquisitely accurately at the same patch of sky all the time. It has to compensate for things like solar light pressure, etc. But it doesn't do it perfectly. And if you look at the signals, so these are all different pixels that belong to the same star over a 3-month period, where the y-axis is very much blown up. Then you can see that some pixels behave similar to the other ones, but then sometimes one pixel gets darker, the other one gets brighter. So this comes from the fact that the telescope doesn't exactly point the same direction, and as the telescope even shifts by a fraction of a pixel, certain pixels get brighter, others get darker. So there are these errors from the telescope that affect, together with the true signal, our measured signal y. So we measure y, we really want q. We don't know n. How do we do that? It looks like an impossible problem. Now the nice thing, what we can do to help solve this thing is, we can notice that actually we're not just observing one star, but we are observing 150,000 stars. And we can hope that these other stars are affected by the same noise sources. So we're going to assume that these other stars are affected by the same noise sources, and also we will assume that these other stars are actually independent of the star that we're interested in. And also these measurements of the other stars will then also be independent of this quantity that we want to reconstruct. And also we will assume that this signal will be independent of the mechanism that distorts it by adding noise. So if taken together all these things, we get certain independence properties, in particular the independence between Q and these other measurements. And then we can come up with an interesting idea for how to try and reconstruct Q. And to motivate this idea, I want to show you a simpler problem, which we call the milkman problem. The milkman problem is the following. So let's assume you have a family with, so there's this statistics, which are probably not true, that up to 20% of all children have a father different from the person they think is their father. This is probably not true, but it's a nice model for this here. So in this case, for instance, we have these 5 children, and maybe we could try to guess which one is, so in England people say this is the milkman's child for such a child. So in this case, maybe it would be easy to guess which one is the milkman's child. But our problem is a little bit harder, because our problem is, not only do we want to know, well, we actually don't want to know which one is the milkman's child, but from a set of children, we want to reconstruct how the milkman looks. And the approach will be, essentially the approach will be, we will try to explain a child, the child of the milkman, in terms of the other children. And whatever we can explain must be things that are due to the mother, and then what's left should be the father. So that's roughly the idea. And we call this approach half-sibling regression because obviously, so in this case, so here, these two measurements, the star of interest and the other stars, they are half-siblings because they're affected by the same noise source. Or here, these children are half-siblings. Okay, so now the idea is actually that's the same graph as before. We have this independence, x is independent of q. We know that x and y share information because they are affected by the same noise source. In fact, they share information only through this noise source. And now the idea is we try to predict y from x. If we do that, it should be possible better than chance because they're both affected by this noise source. But whatever we do with this, we won't be able to remove anything about the signal because x and q are independent. So whatever we can explain must be due to the noise source. So our idea will be to remove the explanation of y in terms of x, for instance by regression, from y to reconstruct q. And to make this easy, we are making the assumption that I talked about before, assumption of additive noise that we use in causality. So we will assume that y is actually, so the measured star is the true star plus some function of the noise. So this is our additive noise model. And secondly, we will assume, so actually, and I should say the role of the noise and the signal has changed here, but it doesn't matter. Secondly, we assume that these other stars, x, they contain all information that we need to reconstruct the effect of the noise. So that means there exists some function of psi that we don't know, such that the effect of the noise, f of n, is equal to that function of x. So all the information about the noise is here. If these two assumptions hold true, and this independence, then we can prove that by subtracting the regression or the conditional expectation of y given x from the measured y, we reconstruct q up to its expectation. And this is an equality of random variables. So it's not just equality in distribution, but this is almost surely correct as equality of random variables. And of course, we cannot reconstruct this expectation because there's just no information about it there. But up to this constant offset, we can reconstruct the unknown random variable. Now you could say this is a somewhat strong assumption that we have complete information in this x, so we can actually weaken this a little bit. So if we drop this assumption, what we get is the following. So before I was saying that this y minus the regression, so call it q hat, this is our estimator for the unknown star. So this estimator for the unknown star is equal to the unknown star up to the expectation. So now we get a slightly weaker result, which says that our estimator for the unknown star, so the difference between the estimator for the unknown star and the actual unknown star up to its expectation, quadratic, this difference is equal to the expectation of the conditional variance of the effect of the noise given x. So if it's the case that from x we can perfectly predict the effect of the noise, then this quantity will be 0. If the information is incomplete, then this thing will be non-zero, but still we can, whenever this is small, we have reason to believe that our estimator is close to this quantity, to this unknown quantity. So that's nice, and there's some more results that maybe we don't have to go through in detail. So one result, for instance, is if we now make some assumption about how the other stars are generated. So for instance, if we assume there are also some effect of the noise, could be different effect, doesn't have to be the same function as before. So before we had f, now we have g. So there are some function of the noise plus some other stars. It's a reasonable model. We can prove that if either the magnitude of this other star goes to 0, or if this is actually a random vector whose components are jointly independent, and then whose dimensionality goes to infinity. So under these kind of conditions, we can prove that we get perfect recovery in the limit. Okay, so this is now an example of how it works. So this is the sort of the data, the raw data, which we are trying to explain by regression on the other stars. The red line is the regression. And then our results are those here. So here we have time. I think this is in days. And this is normalized in some sense that 0 is the mean. And then whenever there's, in this case, a relatively pronounced exoplanet transit, you see these spikes going down. And this is our result. This is sort of the standard result. It's called the pre-search data conditioning. This is what the astronomers do. And as you can see, we have removed a substantial part of these additional fluctuations that contain no information about these transits, but in some sense just disturb the signal. And so this is just an anecdotal thing, but we can also give a statistical evaluation. And our system is the red one, and this is a certain quality measure that the astronomers call the combined differential photometric precision. And you can see that this quantity for all ranges of stars, these are star brightnesses, tends to be better for our system than for their gold standard that they normally use. And so with this, I want to gradually wrap up. So I try to convince you that maybe it's not the full story to only look at statistical dependencies. There are some interesting cases where you should be doing more. And I briefly mentioned to you before this definition of a cargo cult. So in some sense, I think we have become very good at generating IID data that are representative of the kind of problems that we want to solve. But it's not the full story. And if we think about where statistical dependencies come from, I think in the end they all come from, they are all results of physical processes happening in the world, often time-dependent processes that run for a while, that generate a dependence between certain random variables. At the end, we have the dependence. And if we only look at this dependence, then we forget that there's a lot more structure in these problems. And so my point of view is that in standard machine learning, it's often enough to imitate the exterior of a process. So we can ignore the causal structure. But if we look at non-standard problems, and I think this exoplanet problem is such a problem, or problems like semi-supervised learning or covariate shift, then we can benefit from looking at causal structure. So we're still working on this astronomy method. It's quite an interesting problem. It became even more interesting because this satellite, I think 2 years ago, or 1 or 2 years ago, one of the reaction wheels broke. One of them had already broken earlier. It had 4 reaction wheels to control the thing in 3D. And now it only has 2 left, which means it cannot be controlled anymore. But the astronomers came up with a clever method to use the remaining fuel in the thrusters to control this spacecraft. So now we have much bigger systematic errors, and they're looking at other parts of the sky, which is interesting because they haven't been analyzed yet. And we used a method related to what I showed you today, but enhanced also by some tricks for searching for exoplanets, because I didn't tell you how to actually find these shapes. So something like this we used, and we found a list of candidates, and quite a few of them have already been confirmed by other methods. And in a few years, hopefully, there will be the next mission by NASA. It's called TESS, which will monitor only the nearby stars, which is very interesting. So Kepler, I told you before, was going up to 3,000 light years only in one direction, but TESS will monitor all the nearby stars to find which ones have exoplanets. And it's very interesting because, I mean, we don't know if we will ever, or anyone will ever travel there. It's still quite far. It's still tens of, or probably most of them tens of light years. But if anybody ever travels there, they will probably travel to a planet that was discovered by TESS. So with this, I want to finish and thank all my collaborators.
Thank you for the wonderful explanation. And do you have questions?
In this Kepler example, if I understand correctly, the noise was a systematic one, right? It was a type of bias. So was it assumed that there is no random noise at all? And if there is random noise, how would it influence all this model?
No, there's certainly this. We don't exclude random noise, so it's perfectly allowed for the noise to be random. But of course, if the noise is random and it affects the two branches separately, differently. So if it affects these stars differently from these. So for instance, if it's a random temperature fluctuation, it might affect both stars the same way. If it gets hotter, then maybe the noise goes up on both sides. If it's a random fluctuation that acts differently on the one star than it does on the other stars, then this kind of effect will be difficult to pick up. So we can only pick up things that act the same way in both directions. I think that's what you're suggesting, yeah.
First, thanks for the great talk. You talked about how you can use observations of different stars under the same noise model. I was wondering if you could comment on the practical or theoretical implications of using different noise sources on the same star, the same Q, i.e. with different telescopes.
It's an interesting question, yeah. So it doesn't. Yeah, I think one should be able to do something for that as well. It wouldn't be exactly the same model, but I think it would be interesting. I mean, of course, in some sense, astronomers do similar things. They do multiple observations on the same object, but then they mostly just average them or to compute a median or something like that. So it would be potentially interesting to think about whether we could do something better if we have additional knowledge about which noises are independent, which are not independent. So it's possible that people have something clever, but I'm not sure. I don't think it has ever been systematically studied from the point of view of causality. Yeah.